How stiff are your poles? Traffic light posts might be deflecting too much in the streets. Stay tuned for the rigid details at 11. This just in. Traffic light posts today are made of AISI 1020 steel, but are they deflecting too much to be safe anymore? I'm here to tell you yes. A group of researchers from the University of Waterloo have put together some information telling us why we should be using 1050 steel instead. They have put together some background information, mathematical evidence, and a process to implement the post. To effectively complete the material selection, we had to go through a few steps. The first being to find the requirements of the post to make it function. The most important feature we thought of was the stiffness of the post. It should not deflect too much under great wind gusts. It should also not fail under the weight of any street light that happens to be installed on top of it. AISI 1050 steel was compared to current materials to determine whether this material is a realistic alternative.
In industry today, there are currently two types of steel acceptable according to the AASHTO, ASTM A572 and A595. These steels are made up mainly of iron, carbon, phosphorus, magnesium, and sulfur. This type of steel is very strong, very cheap, and very easy to work with in lower temperatures. The process involved is very straightforward: cold working, welding, and then galvanization before it's finally sent out into the field. Now let's just see how they came up to this conclusion that there's a better material out there for the job.
Thanks, Ryan. So, to formulate how we come about to choose this material, we thought, well, we've got to optimize two of the material's characteristics, the stiffness and the compressive strength. So to get the stiffness, we use these four equations here. We treated the pole as if it's going to be thin-walled because we know that the ratio between the diameter and the thickness would never exceed 1/20. So here we're looking at the wind load at the top of the light post and the impact that that might have on how much the light post bends. We're able to formulate this MPI here with the geometric constraints and the functional requirements, which will lead us to a slope for the post. The other thing we calculated out was the compressive strength. So here we took into account the weight of your average light post being about 220 pounds. Now, if you want a safety factor of 2 and real people units, it gives you about 1960 newtons to account for. So we're using that as our critical force. We were able to formulate another MPI which minimized mass as well. Using these and a couple other techniques, Alex will show you exactly how we came about choosing our material.
Given the MPIs that I introduced, I used CES EduPack to apply them to all known materials and narrow down the list to roughly 2,000, as you can see in this figure here. Constraints such as price, density, processing properties, and percent elongation, on top of the compressive strength and stiffness from the MPIs, we were able to narrow the list down to roughly 4 steels, as you can see here. These 4 steels had carbon contents ranging from 0.4 to 0.5% carbon. Due to the similarities between the steels, we used the one with the highest percent elongation, which happened to be AISI 1050 steel. This steel, as you can see here, was water quenched and tempered at 315 degrees Celsius. This tempering produced the percent elongation that I explained, which happens to be roughly 10 to 16%. By looking at this table, we can see properties such as price, density, and some other mechanical properties that we don't need to go into details now. This next slide shows properties such as processing. For example, this metal can be hot formed, cold formed, and welded fairly well as it's able to withstand environments with fresh water and weak alkalis. Next, Ryan will talk about the processing of this material.
The steel we've chosen is actually very similar to the one currently being used. You'll see the number comparisons in a bit. So naturally, they have very similar processes. Large rolls of the steel would be brought to the processing plant where the sheets are cut to length, and it would either be pressed to create several angles, which would form a near cylindrical final product, or it would just be formed into a cylinder by rolling it. The seam would then be welded shut, and the now cylindrical steel pole would have the base plate welded to the bottom. The base plate is the part that would be bolted to the concrete at the intersection where it's installed. After the base is attached, the unit would be moved to the galvanization stage. Galvanizing the post is a relatively cheap and effective way through reducing the risk of corrosion. First, the pole will go through a series of acidic baths to remove any contaminants that may negatively impact the effectiveness of the galvanization coat. After being cleansed, the post is submerged in a vat of molten zinc. This is a galvanizing material that protects the steel from corrosion. The pole is then ready to be installed and used to support traffic light signals.
So, when you look at the comparisons between the AISI 1050 and the AISI 1020, you'll notice that they're both about the same price, they have about the same density, and their Young's moduluses are fairly comparable. The real difference comes down when you get to the yield strength. The yield strength for our proposed AISI 1050 steel is about 2 and a wee bit more times as much stronger. This is a lot of good factors to it because it means that if a car bumps into it a wee bit, you're not going to have to replace the whole light post. It's not going to come crashing down on anyone. It's pretty strong. That means you don't have to replace it as much, which does save money in the long run. So that's less tax dollars spent. Now, if you look at the percent elongation, you might think it might not absorb as much impact if a car crashes into it. But at the end of the day, the fact that the light post won't hit the ground saves other people, potential civilians, who wouldn't otherwise be involved in a car accident. One of the downfalls of the 1050 steel is that it has less than optimal performance at low temperature, meaning that if it gets to below -10 regularly where you are, it's maybe not what you want to use. So we'd recommend using this in the more tropical areas of the world, somewhere nice, near a beach. And really, at the end of the day, that's it. Our steel is a lot stronger for a couple of reasons, and that's why you should go with it. And over.
No, fuck.
Wow, that was really great news, guys. Thank you so much. I learned so much about metals and light posts. But here at this news station, we have to ask the real question. Is it worth it?
Well, I don't think it's worth it to retroactively implement anything or go tearing down light posts, but the next time someone in Florida who's 100 years old drives over a light post, put it in with something stronger. It might save you a wee bit of money in the long run.
That's completely fair. We have to thank the University of Waterloo for providing these research to do all this amazing work. Next time, stay tuned for more relevant information like weather and traffic and politics and such.